So today we'll be studying about screw jack. But before we do that, we see here that screws are used for fastening purpose or for transmitting power or motion. Now for transmitting power, we see that a square threaded screw has a greater efficiency than a V-threaded screw. So we won't dwell into this topic much here. Instead, we will keep our discussion restricted to square threaded screws only. Okay, so now we come to a screw jack. Okay, so this is a very simplified diagram of a screw jack. I have shown here the frame of the screw jack and the screw of the screw jack. Okay, now this screw has external threads on it. Now these threads slide up and down the internal threads on the frame. Okay, now here I've shown the free body diagram of the screw, but I haven't marked the forces yet, so we'll do that in a bit. But before we do that, we see here that the screw has square threads here, as we know that square threads are the most efficient for transmitting power. Okay, now the screw is under the action of an axial force, okay, W, and a moment M. Okay, so this force and the moment are applied on the screw. Okay, now R is the mean radius. This R I've shown here is the mean radius. So mean radius is nothing but the average of the crest radius and the root radius. Okay, so mean radius is just midway between the crest and the root radius. Okay, now phi is the friction angle. We all know this. So the last point says that the moment M is just sufficient to turn the screw. Okay, so what do we mean by this? This means that the moment M is just sufficient to cause the sliding between the threads on the screw and the threads on the frame of the screw jack. Okay, so in other words, we can say that the screw remains in static equilibrium. Okay, that is summation of all the forces on the screw is 0 and the summation of all the moments on the screw is 0. Okay, so we'll see that in a short while. Before we do that, we come to the free body diagram of the screw. Okay, so first of all, we mark the axial load on the screw. This is acting vertically downwards. Okay, and it is equal to W. There is also a moment acting, okay, like this. Now we see that there is some part of the threads of the screw which is in contact with the threads of the frame of the screw jack. Okay, now from this part also I have taken a small portion and I have represented here. Okay, now I will mark what is the reaction on the small portion by the frame of the screw. Okay, so we see here that this moment M is such that the threads on the screw are trying to climb up the threads on the frame of the screw like this. So they experience a frictional force in the backward direction like this. Okay, and we also have a normal reaction like this from the frame. So we can say that the total reaction from the frame would look something like this. Okay, so we draw it again. So the total reaction would be something like this. Now if this is the common normal, then as slipping is taking place, or just about to take place, we can say that this angle would be nothing but the friction angle phi. Okay. Now this angle is also known. It will be equal to alpha. Okay. So this is your reaction from the frame of the screw jack on this small portion. Okay. Don't forget that. Okay. Now we see here that R has two components. This is the horizontal component and this is the vertical component. Okay. The horizontal component is RH and it is equal to R sine alpha plus phi, and the vertical component is nothing but R cos alpha plus phi. Okay. So now to avoid any confusion, we'll write what is R. Okay. So R is the force exerted by the frame of the screw jack on a small representative portion of the threads on the screw in contact with the threads of the frame. So I hope things are clear now. They will be more clear when we'll do the mathematical analysis. So let's do that now. So the moment exerted by the force R, okay, about the vertical axis is equals to, so now if we look from the top, now this will be the average radius R, okay, and the horizontal component of the reaction R will be acting like this, and they will have angle 90 degrees between them. Okay, so R cross F will give us nothing but R to RH, which is nothing but R into R sine alpha plus phi. Okay, now one thing to note here is that phi is the friction angle. Okay, and we know that mu is equals to tan phi. Okay. Now this is the moment generated by the reaction R about the vertical axis. Okay. Now we should remember that the reaction R is the force exerted by the frame on just a small portion of the threads which are in contact. Okay. So if we write the total moment exerted by all the reactions on the thread, so this is equal to summation of small r into capital R sine alpha plus phi. So we'll sum this up, okay, and this is basically the summation of all the moments exerted by the reactions coming from the frame of the screw jack. Okay, so we have basically summed up all the horizontal components of the reactions, and we have taken their moments about the vertical axis. Okay, so now if we do the summation of this term, we see that R into sine alpha plus phi appears in every term. Okay, so it comes out of the summation. So we are left with summation R. Okay, so let's write this as R sine alpha plus phi into RT, which is the total reaction on the screw by the frame. So now we know that the screw is in static equilibrium. Okay, so we have summation of all the forces in the vertical direction is equals to 0. Okay, so if we take this direction to be positive, so we can write minus W. This implies minus W, and the vertical component of the reaction from the frame plus, now we should use the summation of all these reactions. Okay, as this is just on a small portion, so summation of all the vertical components of the reactions. Okay, this should be equal to 0. Okay, so this implies that W is equals to summation vertical component of R is nothing but R cos alpha plus phi. Okay, now we know that cos alpha plus phi will appear in every term, so that comes out, so W comes out to be cos alpha plus phi into summation R. Summation R we have written as RT. Okay, so W comes out to be cos alpha plus phi into RT. Okay, now as the screw is in static equilibrium, we can also say that summation of all the moments in the vertical direction should be equal to 0. Okay, so now we see here that the moment M, if we view from the top, is counterclockwise like this. Okay, this is the moment M. So if we take counterclockwise to be positive, then we have, so this will imply M minus the moment generated by summation RH. Okay, it is clockwise, so it will be minus, what is the moment? R into RT sine alpha plus phi. Okay, so this should be equal to 0 as the screw is in static equilibrium. Okay, so this is another equation we obtain. Okay, so let this be the first equation, this be the second equation. Okay, now what we do is, let's do it here only. So what we do is, we divide the second equation by the first equation. So we have M by W is equals to small r into tan alpha plus phi. Okay, so this implies that the moment M is equals to W into small r tan alpha plus phi. Okay, so we are done here. Our next job is to find out this angle alpha. Okay, so what is this helix angle alpha? We'll do next. Okay, now to determine this helix angle alpha, what we do is, we unwrap the thread of the screw for one complete turn. Okay, so this is the thread for one complete turn. Now for one complete turn, this length would be 2 pi into r. Okay, r being the mean radius, and this length would be L, which is the lead of the screw. Okay, and lead is the advancement of the screw for one complete turn. Okay, so this is the lead, and this angle will be nothing but alpha. Okay, so we can have tan alpha as L divided by 2 pi r. Okay, or alpha is obtained as tan inverse L by 2 pi r. Okay, so we get the helix angle. Okay, this is the helix angle. Okay, now this unwrapping has given us an idea. What we can do is, we can unwrap the entire portion of the thread of the screw which is in contact with the frame of the screw jack. Okay, and we can imagine this as a weight W which is kept on a rough inclined plane with an inclination angle alpha. Okay, now this weight can slide up or it can slide down the inclined plane. Similarly, this thread can slide on the thread of the frame of the screw jack up and down. Okay, so we have developed a model in which the portion of the thread of the screw which is in contact with the frame of the screw jack is acting like a weight on an inclined plane, going either up or going either down on that inclined plane. Okay, now we see on this portion of the thread weight W is acting. Okay, and we know if this thread is sliding up on this incline, then frictional force will be backwards and the reaction from the frame will be R total, and it will be oriented like this, and this will be having an angle phi with the common normal. Okay, and one more force is acting on this thread, that is because of the moment applied. Okay, so if this force is P, then we know its magnitude will be m by r. Okay, so now we see that this angle is alpha. Okay, so this angle will be alpha. We know that these three forces are concurrent and they can be drawn like this. Okay, we know that this angle is 90 degrees and RT is forming angle alpha plus phi with the vertical. Okay, alright, now this will be pi by 2 minus alpha plus phi. Okay, so we can write the relation here that RT divided by sine 90, that is 1, is equals to W divided by sine of pi by 2 minus alpha plus phi, that will be cos alpha plus phi is equals to P. Okay, now P can be written as m by r, so it is m by r divided by sine of alpha plus phi. Okay, so we see here that this gives us the relation m is equals to W R tan alpha plus phi. Okay, so this relation we got earlier as well. Okay, so our model is fine and it works. Okay, now we come to a concept called self-locking. Okay, now if we remove this force P, then only the weight and the reaction from the frame will be there. Okay, so this is very similar to this problem. Okay, a weight W is on an inclined plane. Alright, now if we draw the free body diagram of this weight, then obviously mg will be acting downwards, normal reaction will be acting like this. Okay, it will have a tendency to slide down. Okay, alright, so the frictional force will be backwards. These are the only forces. Okay, now we see that if this angle is alpha, then this angle is also alpha. Okay, so we break this into two components. This will be mg sine alpha, okay, and in this direction it will be mg cos alpha, okay, and we remove the original force. Okay, now if this block doesn't slide down on its own, then F must be greater than mg sine alpha. Okay, now the greatest value of F can be mu n. This should be greater than mg sine alpha. Okay, when this mass will have a tendency to just slide down the incline, then the frictional force will be equal to mu n. Okay, so mg sine alpha should be less than mu n to not cause the sliding of this mass. Okay, so n from this can be calculated easily as n is equals to mg cos alpha. Okay, so mu mg cos alpha is greater than mg sin alpha. Okay, which gives us mu is greater than tan alpha, and mu can be written as tan phi in terms of friction angle. So tan phi should be greater than tan alpha. Okay, so we come to a conclusion that for the screw to be self locking, the condition is phi should be greater than alpha. Okay, this is the condition for a self-locking screw. So if the screw is self-locking, then even if we remove the force P, then also this thread won't slide down on its own. Okay, so irrespective of the axial weight applied on the screw, this won't slide down. Okay, if it is a self-locking screw. Okay, so if this screw is self-locking, then to unwind it we have to apply a force P in the opposite direction. Okay, so let's do that. Now if the screw is self-locking, then you have to apply a force which is in the opposite direction. This is the weight. Okay, now this thread will have a tendency to slide down, so frictional force will be upwards. Okay, so the reaction from the frame would be like this. This will be phi. Okay, now if we extend the vertical line, then if this angle is alpha, then this angle will be also alpha. So this angle is phi minus alpha. Okay, so we have W vertically downwards like this, P is acting like this, and this is RT. Okay, obviously this angle is 90 degrees. Now RT has an angle phi minus alpha with the vertical. So this angle will be phi minus alpha. Of course, this angle will be pi by 2 minus phi minus alpha. So if we write the relationship between WP and RT, we have RT divided by sin 90, that is 1, is equals to P by sine of this angle, which is sine phi minus alpha, is equals to W by sine of this angle, which is cos phi minus alpha. Now we know that P is nothing but m by r, so we write it here only. This is m by r. So this implies that m is equals to W r tan phi minus alpha. Okay. So this is for lowering of the load. So if this screw is self-locking, then we have to apply a force P to lower this load. Okay, and this is the relation. All right, so M is equals to WR tan phi minus alpha. So we had for raising of load phi plus alpha. Okay, so this is for the condition when phi is greater than alpha. Okay, this is for a self-locking screw. Okay, now what if this screw is not self-locking? Phi is less than alpha. What if this is the case? So if this is the case, then the screw is not self-locking. Okay, this implies that the thread will slide down on its own. Okay, so if we have to stop it from sliding down, then we have to apply a force in this direction. Okay, let's see. So weight W is acting like this. Now to stop it from sliding, we have to apply a force P. Now if this is the common normal and this is the vertical, we have angle alpha between these two. Okay, as this angle is alpha. Now we know that this thread has a tendency to slide down, so frictional force will be upwards. Okay, and we know that phi is less than alpha in this case. Okay, so RT will be acting something like this. This will be RT. Okay, and this angle will be phi with the common normal. Okay, so this angle will be alpha minus phi. Okay, right, now we can draw these forces. So W will be acting downwards like this. Okay, RT is acting like this, and this will be P, which is nothing but m by r. So we know that RT makes an angle alpha minus phi with the vertical. This is 90 degrees. This will be pi by 2 minus alpha minus phi. Okay, so again we have the relation m by r divided by this angle, which is nothing but sine alpha minus phi. Okay, is equals to RT by sine 90, that is 1, is equals to W by sine of this angle, which is nothing but cos alpha minus phi. Okay, so again we have the relation M is equals to W R tan alpha minus phi. Okay, this was phi minus alpha, now we get alpha minus phi. Okay, so this is the relation. So this is the minimum moment we have to apply so that this thread doesn't slide down on its own. Okay, so this is it with respect to screw jack. Okay.